today's video, here is a nice problem regarding arithmetic numbers. Here is the following setup. We have this capital A sub n, which equals 2 to the 3 to the n plus 3 to the 6 plus 2 plus 5 to the power 6n plus number 2. Okay, so the main goal, we are going to determine the greatest common divisor for these terms: a0, a sub 1, all the way down to the a sub 1999. Okay, let's start with a sub 0. So we get a sub 0 here, which is going to give us number 1 as you're replacing n with 0. So we get here 3 to the 2 plus 5 to the 2. This one, it simply is going to give us 35. So 35 is same as 5 is multiplied by 7. Okay, so at this point we cannot decide the greatest common divisor, because we got 5, 7 here and 35. We don't know yet which one is a common divisor. Now let's move on to the second obvious case, 1. So a sub 1, it's more simple as by replacing n with number 1. So I get 2 to the 3 plus 3 to the 8 plus 5 to the 8. Okay, so since we get 35 here, we get 5 and 7 and 35, which means the greatest common divisor between these terms, it could be 5, it could be 7, it could be. Now let's try each of these. Let's reduce this to mod 5. For sure we will have kind of relationship between the first case and the second case. So since we have the product 5 and 7, we are going to try mod 5 and mod 7 and decide which one is going to be GCD here. Okay, so reducing this one to mod 5, so I'm going to see 2 to the 3, which is equals 8, is the same as 3 mod 5. Okay, now let's go ahead and move on to the second term, which is 3 to the 8. So it's more simple, 3 to the 8, which equals 3 square, all is raised to the number 4. So if I'm going to reduce this one to mod 5, we know this is 9, we'll have negative 1 mod 5, because we have, which is a congruent to minus 1 all raised to the 4, which is a congruent to 1 mod 5. Let's move on to the last one. Last one, it's clearly is 0 because you reduce this one to mod 5. Now let's put this one together. So you get a sub 1 is a congruent to 3 plus 1, which is 4 mod 5. This one is clearly, since we have number 4 as a reminder here, which means 5 cannot divide this one, which means 5 is not the common divisor here. Okay, it's not a GCD. Now let's check 7, okay, for this one. So I will have the same argument. So for 2 to the 3 is the same as 1 mod 7, because you have 8 is 1 more than 7. So let's check the other one, 3 to the 8, which equals 3 squared, all is raised to number 4. I will have the same argument here. So we get 3 squared here is a congruent to 2 mod 7, because you have 9 is 2 more than 7. Okay, so it's clearly this is 2 to the 4. 2 to the 4 is 16. 16 is 1. 16 is 2 more than 14. So I get a reminder number 2 here, mod 7. Let's try the last one, 5 to the 8 as 5 squared, all is raised to the 4. You know 5 squared, I get a reminder 4, all is raised to the 4. We know 4 to the 4 is the same as 4 squared, all is raised to the number 2 here. We know 4 squared 16, 16 is 2 more than 14, which is 2 to the 2, which is 4 mod 7. Okay, so adding these three statements together, I get 1 plus 2, which is 3, 3 plus 4, which is 7. So I get clearly a sub 1 is a congruent to 0 mod 7, which means 7 divides this one, and also 7 divides first one. Okay, which means it's clearly, it seems GCD of these two terms is 7, but we need to check the general case. Now let's get rid of this one and move on to the general case. We had a nice exploration here to determine the GCD of this bunch of these terms. So as I said before, we know 2 to the 3 is a congruent to 1 mod 7. So it's more simple. This one is going to give us 2 to the 3n is a congruent to 1 mod 7. Okay, let's check the second one. Okay, 3 to the 6 is the same as 3 squared, all is raised to the 3, like this. You know 3 squared is a congruent to 4 mod 7. So this one is a congruent to 4 to the 3. We know 4 to the 3 is 64. 64 is 1 more than 63. 63 is divisible by number 7. So we get 1 mod 7. Now we are going to work on this one. So I get 3 to the 6 and plus 2 is the same as 3 squared is multiplied by 3 to the 6, all is raised to the n, is the same as 3 squared is multiplied by 3 square, all is raised to the 3, all is raised to the n as a power. Okay, so it's more simple. So reducing this one to mod 7, it's clearly we have 9 here. 9, it was 2 mod 7, so this is 2. So it's clearly is 2 here. You have 2 to the 3. 2 to the 3, it was 1. 1 is multiplied by 2. It's clearly to the 3, it was 1 mod 7. 1 to the n, which is 1. 1 is multiplied by 2, which is 2. So we get 2 mod 7. Moving on to the last term, which is 5 to the 6 to the 6n plus 2. I will have the same thing here. I get 5 squared is multiplied by 5 squared, all is raised to the 3, all is raised to the n. It's more simple. 5 squared, which is 4 mod 7. So get here 4. This one, it was also 4. 4 to the 3, which is 64. 64 is 1 more than 63. So get 1 to the n, which is 1. So get 4 here, mod 7. So adding these 3 statements together, I get 4 plus 2, which is 6, plus this one, which is 7. It's clearly is going to give us 7 divides a sub n. Okay, so in particular, if you take n equals 1999, of course you will be verified this one, because n, it can be any integer, it satisfies this condition. Okay, now since we're applying this regular method on this one, reducing this expression to mod 7, you can use the Euler formula. Euler formula, it's more simple to apply it on this one here. Okay, then apply the Euler formula here. A to the phi to the n, which is a congruent to 1 mod n. So with this tension function phi of n, which equals n factorization prime 1 minus 1 over p1 is multiplied by 1 minus 1 over p2, and all the way down to the 1 minus 1 over pk. Okay, those p1 through pk are factorization primes. For our example, taking n equals 7, replacing n equals 7, we will determine this one, phi of n, which is phi of 7. Phi of 7 here, check 7 here. So I'm going to replace n with 7. So we are going to stop here. This one, all this one is not gonna, because I will have only this one. Because 7, it will have only, we are taking only the divisors of 7. Okay, only the divisor of 7, which is 7. Okay, so the primes, we are replacing p1 with 7 here. So it's more simple. 1 minus 1 over 7 is going to give us 6 over 7. Okay, this is 6 over 7. Multiplying this one by this one, so I will be ended with phi of 7 equals 6. Okay, so I'm going to replace this phi of 7 with number 6 here. So it's more simple. A will be replaced with 3. So I get 3 to the 6, which is this one, is a congruent to 1 mod 7. Exactly. Okay, 7. Also, this one is going to be the same thing for 5 if you replace 5 here. So get 5 to the 6, 5. But remember here, GCD of this base A and N must be equals 1. Okay, just the condition we are going to hold, this GCD of the base A, okay, and N must be comprimed, their GCD equals 1, because 3 cannot divide 7 here, also 5 cannot divide 7. Okay, so we will have the same, we will find the same results. So at the end, GCD of this one must be equal 7. Okay, so I've done this problem. Thank you for watching. I will see you next video. Bye.